Alrighty, let's talk about when a double replacement reaction occurs and what that looks like on the particle level. So on packet page 15, you'll see this example. Make sure you have your periodic table out and your solubility chart, as we'll be using both of those today. So looking at this example here, I have aqueous potassium carbonate and aqueous iron 2 sulfate reacting here. When these two substances mixed together, iron is going to trade places with potassium, and since it's bonded to sulfate with no extra subscripts here, I know that iron is going to have a +2 charge, and then it's going to bond with carbonate. If you look on the back of your periodic table, you'll also notice that carbonate has a -2 charge. So I don't need any extra subscripts since these charges cancel each other out. They go away. The other product I'm going to have is when potassium, the +1 charge, bonds with sulfate that has a -2 charge. Now these charges do not cancel out, so I need a subscript of 2 with potassium, and then they go away. So to figure out whether or not this actually occurs, if we see a chemical reaction happening, we need to use our solubility chart. So taking a look at this, I'm first going to check that first compound. If you notice down below, I have iron +2 and iron +3. So please pay attention. We're going to be using iron +2 in our example here. And then I'm going to see, well, what happens when it matches up with carbonate? So when they line up, their state of matter is going to be solid. So going back to this example, I'm going to put a little S next to it. Let's check for our second product here. So potassium sulfate. So I don't see any potassium on our solubility chart. It is actually hidden under group 1. So any element in group 1 on the periodic table, hydrogen to francium in that first column all the way on the left-hand side, those are going to be kind of hidden underneath this group 1 here. So I look at group 1 and then I look at SO4, and where they match up is going to be aqueous. So this reaction is going to occur, and I'm actually going to box in our precipitate here. And it'd be good to get into that habit because this tells us that a precipitate forms and then a reaction does occur. So taking a quick second to go through and look at this, we actually don't need to change any coefficients here. They're all going to be coefficients of 1. So let's see, what would this look like in the lab? And if we were to draw some particle pictures, so that's our balanced chemical equation up above. And now whether I have pipettes or beakers filled with our aqueous solution. So remember, they kind of look like water because they're dissolved in water. So let's write that down. AQ means to be dissolved in H2O. I'm actually not going to draw the H2O particles here. We're going to look at that second semester, what the interactions are really happening with that water molecule and how it can kind of dissolve and break these apart. So I'm just going to focus on the ions because potassium is a metal and the carbonate polyatomic ion is going to be considered to be our nonmetal. So if I look at my formula, for every 1 potassium ion that breaks down, I actually need 2 potassium ions because in our chemical formula there are 2 potassium ions for every 1 carbonate anion. So when you look at the chemical formula, it tells us the ratio of anions when they separate and when they dissolve in water. So that's my first reactant. My second reactant is this iron 2 sulfate, and I don't have any extra subscripts here, so they're just in a 1-to-1 ratio. So there's my iron 2 charge, and then SO4 is its -2 charge. So this is a 1-to-1 ratio. Potassium carbonate is going to be a 2-to-1 ratio. And this is really important because when we look at our products, the whole reason why we have the balanced chemical equations is we're looking at these ratios of these ions and these substances together. So if I were to mix these 2 beakers together, we're going to find that we're going to form one of our precipitates, and that's actually going to sink down to the bottom. So you make this like heterogeneous mixture where your precipitate is going to be at the bottom. And for this example, it's that iron 2 carbonate. So I'm not going to break it apart because it is a solid. So I'm going to keep those particles together. I'm going to draw a couple just to show that it is a layer of our solid precipitate down at the bottom here. So then what's going to be floating up above in the solution? And as you saw in your well plates during your double replacement lab the other day, you saw that maybe you had some solid stuff floating around and then you had what looked to be liquid. So what's left over? What didn't make it into the precipitate? Well, that is our potassium and our sulfate. So K2SO4 is our aqueous byproduct here. And that's what's going to go up over here. So again, if I look at this, this is a 2-to-1 ratio because for every 2 potassiums, I'm going to have 1 sulfate. So let's actually draw that out. So K plus 1, and then 1 sulfate minus 2. So that's what's going to look like. Our aqueous solutions break apart because they're dissolved in water, and our precipitates stay together because they are solid. So will this reaction occur? Why or why not? It will occur, yes, because FeCO3, I'm being very specific here, is a solid precipitate. Awesome. Our next video, we're going to look at what happens to our drawings and our pictures when a reaction does not occur. So join me on the next page for that example.